Oh. Did anyone see my screen?
Yes.
Oh, okay. Hello everyone. We are students from National Taipei University of Technology in Taiwan. Here are our team members, and I'm Yun Shanxue. And our model is built on a basic FNN, and the input layer takes three kind of parameter and frequency, and magnetic flux density, and temperature. And for input data, we apply this score normalization, which effectively minimizes the scale difference between various features. And the output of our model is PCB, and relay setting of the model are as shown in the table on the bottom right. And to find the optional hidden layers and hyperparameter setting for our model, we utilize the optional tools for optimization. The final result we obtain are shown in the table below. And in the final test set for some material with less data, we use transfer learning to address this issue. Pre-trained models are beneficial because they have already learned valuable features from large data sets. Regarding how to acquire a pre-trained model, we consider that if the core have similar pH curves and core loss under the same frequency, temperature, and excitation source, it indicates they share similar core characteristics. So we use a way called dynamic time warping to determine whether the 5 unknown core materials have a similar to 10 known core materials. For example, in the bottom right graph, we have material sit at 316.45 kilohertz and 90 degrees temperature. For loss around 1,832.082 with a 10% margin, we identified pH curves and their corresponding core materials. And next to each material name, there's a DWT value. Lower DWT values indicate a higher similarity in the pH curve. However, we haven't yet found effective method for classifying waveforms. So in this approach, there are still some shortcomings. And the final result shows the material D and E did not perform as expected, and each material model had a large number of parameters. This could be due to an excess of parameters in the FNN, leading to overfitting. Additionally, directing input the magnetic flux waveform might have also contributed the large parameter count. Furthermore, transfer learning did not identify suitable training models for these materials.
For D&E, so for D&E, you didn't find good match.
Yeah. Okay. So this is our future work to further optimize transfer learning technology and for small data sets to increase data volume for short data arguments. Additionally, consider the limits of a simple FNN model in handling large data sets. We plan to explore combining it with other model architecture for further observation. And in fact, this was our team's first year in turning machinery. So we are very grateful to the MagNet Challenge organization team for hosting this competition. Although our team results were not outstanding, but we learned a lot in this competition. Thank you.
Yeah, no, winning is not a purpose at all. So I would say this is the game in the end. Don't think about the result by too much. Yeah, it's and also many times I believe may just be the performance not so great, just maybe a coding error, maybe some teams made some mistakes, or maybe just missing one step. For example, normalization you didn't normalize in the right way, or so I would say there are many reasons for not getting great results, and that doesn't mean that your approach is not great. I really like the dynamic waveform wrapping methods. I think as we discussed yesterday, There are advantages of trying to look for a similar material and start from there. And there are also advantage of not doing that, because there could be a material which is just no similar material at all in the future. So I would say that's why we need a community to try all the different methods and understand their strengths and limitations.
Oh, okay, thank you.
Great. Any other question, Haran, Shukai, and the audiences?
Yeah, I think just as you said, for the material D and E, it's not working that good as the previous three materials. I think it's most likely to be the overfitting. I feel like, because for material D, we intentionally took out a majority of the trapezoidal waveform, and for the material E, we took out a part of the frequency and the flux density. And in this case, it's very easy for the neural network to get overfitted into the training set, because this is like we intentionally downsample we sample the data set in a specific way, so that if you have a large neural network, and it's very easy to get overfitted into those, and that's why for those testing points that never seen by the neural network, it may not perform that good, I think.
Right. And the other thing I noticed is that you are considering B on the same level as similar information as F and T. So that's something maybe you want to consider improving, because if you look at your input parameters, the majority of input parameters B, and then you have one F and one T. So maybe separating them and feeding them into different layer will improve the result.
Okay, thank you.
Anyway, great, thanks. If we don't have more questions, we can move on to two theoretical equation-based models. One is Mondragon, and the other is Southeastern University. These are analytical branch of methods. Is Mondragon team here?
Yeah.
Yes.
Can you hear me?
Yes.
Okay.